Hello students, this is a quick tutorial on the chapter number 5, which is gravitation. Most of you had not covered this chapter, so I am going to give you a briefing of all the topics that we are going to cover. Actually, the topics that we're going to cover for this chapter, which is gravitation, are basically 5.1, 5.2 and 5.3. These are the three topics as per the reduced syllabus from Federal Board. We're going to look into these topics in a quick succession, and then we're going to do some numerical analysis along with the chapter. I hope that is going to be enough for you to understand the basics of this chapter, and we may continue with our current regime of classes that we're going to have from chapter 6 and onwards. Okay, let's get into the first topic. First topic is actually 5.1, which is the law of gravitation. Right. We do know that there's something we call as gravitational acceleration, right? G, and the value for this is 10 meter per second square. We have used this value in chapter number 2 and chapter number 3. For chapter number 3 we had discussed this in terms of weight, where G was the gravitational acceleration and weight was what we call a force, right? And this G was actually an acceleration, and this is what we have as mass. So we do know that F is equal to ma, so all along in terms of weight we're trying to calculate force, right? Where do we get this G? How do we know that G is 10 meter per second square? This is an acceleration that we know and we believe and we use in daily life. That gravitational acceleration is the acceleration for every falling object that is falling towards Earth, right? So when we are trying to discuss gravitational acceleration, we need to understand that acceleration is due to certain force, right? F is equal to ma, second Newton's law, right? So for any acceleration there has to be certain amount of force behind it. So what is the force that is causing the gravitational acceleration? Let's say we want to know where G is coming from. Where does this G come from? Which force is responsible for this, right? And that force is what we call as gravitational force. It was actually discovered by Newton. You must have heard this old pen prick from a lot of people, and they share this, that it was an apple that fell on Newton's head, and that made him believe that there was something known as gravity. No, that is actually a wrong idea. Eventually it was not the apple that fell on his head, it was actually going to be a moon, the way he was imagining at the moment. He was actually taking a walk in his garden, where he usually used to spend a lot of time looking at stars, making calculations about orbits and stuff, discovering the universe. During that time he thought of this idea that if something is falling, let's draw his dream, what he was trying to actually think at the moment. Consider if this is a tree for us, and here's one apple that is falling right onto ground. What did this why did this apple fall onto the ground? Why didn't it just go here or anywhere else? This is what Newton actually thought at the moment, that what happened to the apple, why it fell down. And then he took up a stone and he threw it around, and it also fell down. And now he wanted to think of a bigger idea. He thought that if the moon, which is revolving around the earth, is it also falling? And that is when he discovered the fact that everything around Earth was falling towards Earth, except Moon has its own velocity because he had already calculated the orbit of the Moon around the Earth. So he was sure how fast the Moon was moving around the Earth and what was the orbit, what was the distance. He knew pretty much that Moon is not falling, but his question was that whether or not the Moon is falling as well. And then he considered the fact that yes, there is some force in nature which is pulling everything towards Earth. And if this is happening with Earth, then why wouldn't it be happening with any other planet like Sun or Moon itself or other planets? You do know that Jupiter has many moons, four of which are very big. Uh, so there is gravitational force which is responsible for pulling the objects towards themselves, and those objects which are able to move around them are obviously moving at very high speeds to maintain their orbit. Otherwise, they would also fall to the planet or the star or any mass that is creating gravitational force, right? So now let's get into the mathematical part of it. Now, as we're talking about the fact that we say this is the Earth, right? And this is an object, an arbitrary object, right? This is M1 and this is M2, right? These are different. I've made them different. You can keep them the same. Let's consider from the center of one to the center of the other. This is the distance which we call as r, right? This is the length which is separating these two masses, right? And we want to evaluate what would be the gravitational force of one object to the other, right? And that is going to be obviously equal. And we want to know the pull or push of each object, right? How they are interacting with one another. This is what we call as gravitational force, right? So in terms of gravitational force, we would say that this force is proportional to m1, where this is m1 and this is m2 over r square, right? The distance between them, the separation between them, the masses themselves, and this one thing which we call as gravitational constant. We will discuss this in a moment. This is the basic relationship for this force. This is how we calculate this force F between two masses, and this is actually happening in everyday life. We're also attracting everything, every object. For example, I'm also attracted towards my computer, and not in a meager way, but in reality, in terms of mathematics, I'm actually attracted to towards my computer, and my computer is attracted towards me because we're both masses, and we're attracted to each other by Newton's law of gravitation. Unfortunately, we would come to notice after doing some mathematical evaluation of these on this term over here, that these masses need to be very, very big, like planets or stars or moon or satellites. Smaller masses like me or my computer are not enough to generate enough force that we could feel it. So yes, there is gravitational acceleration between me and every other mass around me in my surrounding. We're all attracting each other, but we are unable to feel that force because the value is very, very small in this regard. Which in terms of bigger planetary systems or celestial objects like stars, moon, planets, we would definitely get to feel this force eventually, and that is what we call as Newton's gravitational force, right? So to sum it all up, we would say that everybody in the universe attracts every other body in the universe, which is in a way directly proportional. The force is directly proportional to the product of the masses. For example, if we're trying to calculate it for Earth, we'll say capital M-E, and let's say an arbitrary object we're trying to evaluate how much force is going to be there. Let's say let's take the small mass as me, and we do know that the force is inversely proportional to the square of the distance between them. Now this term is very important. This is why this is called inverse square law. And why this is called an inverse square law? Because we do know that inverse proportions, they always decrease when the other quantity is increased. For example, if I increase the radius over here, the force would decrease. If I have the masses, which is capital ME and small m, if I increase the distance between them, you would find that the force between them is also reducing, right? So previously we had written a tiny little alphabet over here, which was capital G, and I said we will discuss this in a moment. Now this is called the gravitation constant. It was obviously calculated by Newton himself at that time. The value for capital G is 6.67 into 10 raised to power minus 11 Newton meter square per kilogram square, right? If I'm not wrong, I guess you're not. That's better, right? So this is the value for G, and this is what we put over here and calculate the forces, right? This is very simple terminology that you have to simply memorize this formula, and you can do a lot with this just one formula. The whole chapter is actually all about this one formula over here, which is the Newton's law of gravitation, which calculates the force of gravity if we know the masses and the separation between those masses, right? So let's do our dummy calculation for this. For example, my let's write data. You can say I'm standing right on top of the earth, right? My mass would be small m, which is around 60 kgs, right? The mass of the earth is about 6 into 10 to the power 24 kilograms, if I'm not wrong. And radius of earth, which is 6.4 into 10 to the power 6 kilometers. This is what we know, right? And obviously the value of G, which is 6.67 into 10 to the power minus 11 Newton meter square kilogram minus 2, right? Now let's solve solution for this. I want to calculate the force that the earth is exerting on me to pull me down, right? That's as simple as we know. So let's try solve this. As we do know from Newton's law of gravitation that F is equal to G M over R square, and mind it, this E over here or over here is a subscript. Subscript means it is not part of this whole letter, but it is representing a significant form of it, right? This is the mass of Earth. This E is not part of the formula, right? This is just for marking that this is what we're talking about is the mass of Earth, right? Just a small one over there. So to calculate the force, let's get 6.67 into 10 to the power minus 11 Newton meter minus 2 kilogram minus 2, right? Multiplied by 6 into 10 to the power 24 kilogram multiplied by 60 kilogram, and this whole thing is going to get divided by 6.4 into 10 to the power 6 kilometers, and we're going to take a square of it. As if you see out of the units that we're going to take a square, so I'm going to raise this square out of here. I'm going to take the square of the value, and I would know that after taking the square my units are going to be squared, right? So this kilometers need to be changed into meters. Sorry, my bad, this is actually in meters. Sorry for this. So if you would know that I can now simply cut out meters square from here, kilograms with these two, so the leftover unit is just newtons, right? So Newton is left. So once I will calculate all the values for this, here's the calculator, let's put in the values. 6.67 exponent 10 to power minus 11, right? We want to multiply this with 6 into 10 to the power 24, and we want to multiply this with 60 and divided by 6.4 exponent 6 whole squared, right? So the answer comes out to be somewhere around 586.23 newtons. Now this is a fun fact, that this is the value what we get. This is the amount of force that the earth is exerting on me while I'm standing right on top of it, right? Since I'm standing right on top of it, this is the whole radius of the earth. If I stand a little higher, then I will actually add more height in this radius and then take the square later on. Keep that in mind, that height will always be added before height to be added before square, right? Before you take the square, remember to add height. If you're not on the surface of earth but higher than the surface of earth, you will have to add height in this formula, and then you will get the right force which is the earth is going to be exerting on you. In this case, as you would know, that we are having this much value of force. Now this is an amazing fact, that if I reverse this equation into doing something else, this is the force that we have at the moment, right? This is the force. This is the force that the earth is exerting on me. We do know that this force is contemplation of what we call as weight. So weight is equal to mg. I do know my mass, which is 60 kilograms, right? We do have weight at the moment, 586.23 newtons is equal to 60 kilograms, right? And this is g as a quantity which we want to calculate. And now simply let's take 586.23 divided by 60 is equal to g, and we're going to get the value of g out of this, right? Divided by 60. So turns out to be 9.77 meter per second square, right? This is the gravitational acceleration, and this is precisely what we call as 10 meter per second square, right? Now you know where this g is equal to 10 meter per second square comes from, right? This is coming from Newton's law of gravitation. We have used this value of g in chapter 2, chapter 3 a lot, and we have never come to the fact where are we getting this value of g from. Now you know where we get this value of g from, right? This is end of topic 5.1. I hope this is enough for you to understand the topic, and if you have any queries, any questions, you can post it in the teams and let me know if there's something else you want to know about this topic, right? Thank you.